Superposition and standing waves. We have so far studied some properties of mechanical waves, including in particular sound waves. What we do in this chapter is to look at what happens when you have more than one wave superimposed together in a certain region. The result is called a superposition. And in particular, when we got two waves traveling in opposite directions, when they satisfy a certain condition, the wave pattern will no longer be traveling, rather it stands still, so we call it a standing wave. Standing waves have many applications in all kinds of areas, including, for example, music. The superposition is a general phenomenon for all kinds of waves, including the mechanical wave. And the most important principle is called the principle of superposition. So what is the principle of superposition? Well, suppose, for example, we look at a certain wave, which is described by y1 at location x and time t. So this is a disturbance caused by a certain source, say source 1. Okay, if source 1 is the only source present, this is the wave, the resultant wave. Now imagine I remove source 1 now, and instead I have source 2 present. The corresponding disturbance would be y2 at location x and time t. Okay, so source 2, if it is the only source present, you're going to have y2. Now my question is, what happens if both y1 and y2 present at the same moment, at the same location? Now, we have never done this before. All we know is that if source 1 is the only one present, this is wave 1, and if source 2 is the only one present, this is wave 2, right? We've never actually put them together at the same moment, at the same time. So what is the result? Well, it turns out that for many waves, not all waves, but for many waves, the result is very simple. It's the simplest possibility, and that is you simply add these two disturbances up to get the net result, y at x and t. Okay, of course, if I had more than two sources, if I had a third source, for example, then I would have, add one more term, y3 and so on. This is called the principle of superposition. Okay, to be exact, this is the so-called principle of linear superposition, because you're just adding them up linearly. You don't square them and take a square root, nothing like that, just linearly. Okay, now it might appear to be something that we can take for granted, but we don't actually do that, because remember, y1 is the disturbance when y2 is not present, and y2 is the disturbance when the source 1 is not present. When both sources are present, in principle, it is possible that both y1 and y2 themselves will change because of the existence of the other source. But nature, in many cases, simply chooses the simplest possibility, and that is just to add them up like this. Okay, if a wave satisfies this kind of linear superposition principle, we call it a linear wave. Okay, not all waves are linear. Some waves are nonlinear, and in particular, if the amplitude of the wave, is large. When I say large, it means it's comparable with the wavelengths. Okay, so this is the amplitude, this is the wavelengths. If these are comparable, then the wave we say has a large amplitude, then chances are that the principle of linear superposition may not work. You have to use nonlinear way of adding these waves up, and that wave is called a nonlinear wave, but we're looking at waves mostly like this, So relatively small amplitude and relatively long wavelengths. Okay, look at something like that. For waves like that, in general, you can use the so-called principle of superposition. So again, this is valid for many waves, even though it's not a universal principle. But we're going to assume that all the waves we discuss in this chapter do satisfy this principle of superposition. In other words, we're considering only linear waves. Okay, so this is the most important principle of our chapter. Let's box it. Okay, it's valid for linear waves. Okay, if the waves are linear, then when we got more than one wave present, I can simply add them up like this. So let's see how we add them up. What's the consequence? Okay, first of all, the simplest type of wave we study is a simple harmonic wave. Okay, So any simple harmonic wave, say y1 equals a sine phi 1. What's phi 1? It is a phase angle, right? It's a phase angle, and since the wave depends on the phase angle as a sine function, we say this is a simple harmonic wave, and a second wave is a sine phi 2. For simplicity, let's assume that they have the same amplitude. If they don't, it won't change the general general idea, but it will make our mathematical calculation a little bit more complicated. So let's assume that these two A's are the same. Okay, you have phase angle phi 1, phase angle phi 2. Okay, these two phase angles differ by a certain amount. Phi 2 minus phi 1, that is the difference in their phase angle, and we call this delta phi. Okay, delta phi. This is the wave caused by source 1, this is the wave caused by source 2. And if both waves are present at the same location, the net resultant wave, according to the linear superposition principle, just add them up like this. Okay, now let us see what happens when you add these two waves up. You can understand that since it's a sine cosine function, right? You know, for two sine functions to be the same, the phase angles do not have to be exactly the same. For example, if phi 2 is greater than phi 1 by 2 pi, or 4 pi, 6 pi, whatever, in other words, a multiple of 2 pi, then these two sine functions will be identical, right? Then we have a term for it. We say these two waves are in phase. Okay, they're in phase. So when one is up, the other one is up. When one is down, the other one is also down. And when the two waves are in phase, they will enhance each other. And here is one such case. Look at the first situation. Okay, here you have two waves, one colored blue, the other is supposed to be green, but that green wave is identical, is exactly the same as the blue wave because the phase difference, delta phi, between these two is 0. Okay, in fact, it doesn't have to be 0, 2 pi is fine, okay, 4 pi, whatever. When you add these two waves up, these two waves are called in phase. Okay, they're in phase because their phase angle differs by a multiple of 2 pi. So when one wave is up, the other wave is also up. When one wave is down, the second wave is also down. When you add them up, you see you get this red wave. Okay, this red wave obviously has twice the amplitude as each of the component waves, so it has a greater oscillation. On the other hand, if two waves differ in their phase angle by 180 degrees, okay, or pi, right, or 3 pi, or 5 pi, and so on, then we go to the second situation like this. Here you have a blue wave like this, right, and the green wave has a phase that's 180 degrees away from it, so delta phi equals 180 degrees. So when the first wave is positive, the second wave is actually negative. It's just opposite to the first wave. Okay. Now, assuming they have also the same amplitude, then at every moment, this wave exactly cancels with that wave. Okay. The resultant wave is therefore 0, like this. So you see, the difference in the phase angle, delta phi, determines whether the two waves will enhance or destroy each other. Of course, in general, the two waves do not have to have exactly either 0 degrees or 180 degrees phase difference. It is also possible that one wave has a phase angle that's 60 degrees away from the other wave. In other words, delta phi equals 60 degrees, or any angle for that matter. So in this case, we have a blue wave like this, right, and a green wave like this. All right, they don't exactly add up to each other or destroy each other, but somewhere in between. Okay, so the result is this red wave like this. Okay, but when we look at the superposition of these waves, we are more interested in the extreme case when two waves are exactly enhancing each other or destroying each other. And here are the conditions that we mentioned. Okay, delta phi, the phase angle, the phase difference between these two waves. If it's 0, plus or minus 2 pi, plus or minus 4 pi, it doesn't matter whether it's a plus or minus, okay? The absolute differences, that's what I'm looking for. Then these two waves will end up with being in phase. In other words, when one wave is up, the other wave is also up. Or when one wave is down, the other wave, one wave is down, the other wave is also down. So you have, they always enhance each other. And then we say they have what's called an interference maximum, okay? interference maxima. What is interference? Okay, that's when you have more than two waves superimposed together in the same region at the same time. We say there is an interference. Okay, how do you know at which point you have a maximum amplitude of interference? Well, that's when these two waves, the phase angle differs by that much. Okay, interference maxima, or we say it's called constructive interference. Okay, constructive interference. Now, again, if the two phase angles of the two waves differ by a multiple of an odd multiple of pi, like pi, or 3 pi, 5 pi, and so on, that means when one wave is up, the other wave has to be down. When one wave is down, the other wave has to be up. So they tend to cancel each other out. Then we say that's an interference minima. The reason why it's a minima is because these two waves tend to cancel each other out. So we also call it destructive interference. Okay, destructive interference. Now, let us look at when you add these two waves up, you have these maxima, you have these minima, right? Now, in most cases, the wave frequencies are, more than a few hertz, which means the wave is going to go oscillate up and down many times a second. Okay. Even mechanical waves can easily have several hundred hertz or even several thousand hertz, such as sound, for example. Okay, if you look at electromagnetic wave, the frequency can be considerably higher. For example, for visible light, the frequency is an astonishing 10 to the 14 hertz. That's 100 trillion hertz. So you got so these waves alternate between up and down very rapidly, many times a second. Okay, so the question is, when you look at a certain point in space, okay, at that point you got, say, two waves, right? At one moment they may enhance each other, but if the next moment they start to have destructive interference, in other words, they destroy each other, then if constructive and destructive interference alternate too fast, then our eyes or ears cannot really discern them, right? We can only discern the average because that happens too fast. Okay, so the question is, how do we make sure that this interference maximum stays as a maximum and interference minimum stays as a minimum? In other words, we want not only an interference pattern, and interference pattern means you got alternating maxima and minima locations. Okay, at this point is maximum, that point is minimum, that's maximum, minimum, whatever. Okay, I want the pattern to be stable. I don't want it to change over time. Okay, how did that happen? Well, you see, to stay at an interference maximum, you want to make sure delta phi stays at these numbers, right? You want to make sure it's always a minimum, then you want to make sure delta phi equals one of those numbers. Okay, and you don't want these numbers to change over time, right? You don't want, delta phi to be 2 pi at one moment and become 3 pi like a millisecond later, because that's going to switch from maximum to minimum, right? So therefore, you want to make sure that delta phi, whatever it is, does not depend on time. Okay, this symbol means independent of time. It is not a function of time. This is the condition for stable interference pattern to occur. Okay, it is otherwise known as the coherence condition. Okay, we say two waves are coherent if they form a stable interference pattern. In other words, alternating maxima and minima patterns that do not change over time. Then we say these two waves are coherent. What is the condition, or what are the conditions for the two waves to be coherent? Let's see. Suppose these are sine cosine waves, okay? Harmonic waves, otherwise known. Then of course phi is simply written as kx minus omega t, actually plus or minus, doesn't really matter, let's say minus, plus phi initial. What's phi initial? That is the phase angle at the location x equal to 0 at the moment t equal to 0. So when you set x equal to 0 and t equal to 0, the phase angle is not necessarily 0, we call it phi initial. Okay, it's called initial phase angle. Alright, so what is the phase difference between these two waves? Well, we plug the phi in. Okay, here is phi 2, right? And here is, actually, phi 2 would be k2x2 minus omega 1t plus phi 1 initial. Okay, actually phi 2 initial. And phi 1 would be k1 x1 minus omega 1t plus phi 1 initial, and so on. Okay, so here's the difference, right? All right, first thing first, I want to make sure that this delta phi is not a function of time. I want to be stable. Okay, if it changes with time, of course, you can go from maximum to minimum and go back to maximum. It's not stable anymore. So what does that tell us? It tells us that we must get rid of this term. All right, we must get rid of this term. We must kill this term. What did that tell you? It tells you that omega 2 minus omega 1 has to equal to 0. In other words, omega 1 equals omega 2. We also call it omega. Just give the common term. This is the first condition for coherence. Okay, so one of the conditions for coherence. They must have the same exact frequency. Okay, and that makes sense. You see, if these two waves go up, down, they always go up the same moment and down the same moment. Then of course they have to turn from up and down simultaneously, which means they must alternate with the same exact frequency. Okay, so that makes sense. Now, these two waves have the same frequency, right? And since they travel in the same medium, they also have the same speed, because the speed of the wave is determined by the medium. All right, so you have the same frequency and you have the same speed. That tells us you also have the same wavelengths. Okay, you have the same wavelengths. Now, what's k? K is 2 pi over the wavelengths, right? And since the wavelengths of wave 1 and wave 2 are the same, that means K1 and K2 are also equal to each other, and that tells me that I can simplify delta phi like this. Okay, K2 plus K1, K2 is equal to K1, right? Let's just simply call it K. K. And then you have x2 minus x1, let's call it delta x. Now, why are these two axes different? Because these two waves could have traveled from different locations. You know, here, wave 1 from source 1, wave 2 from source 2. They have traveled different distance before they arrive at a certain point to interfere with each other. And that one wave traveled a distance x1, the other one traveled a distance x2. Therefore, it is possible that x2 is different from x1. That only tells us they don't necessarily come from the same location. Okay, don't forget there is one last term here, plus delta phi initial. Okay. For the two waves to be coherent, we want to make sure that this expression, which is delta phi, is not a function of time. Okay, it's not a function of time. That's how you have a stable interference pattern. It is clear that this first term has nothing to do with time. Okay, it's k delta x. What about the second term, phi initial? Well, you know, it is possible in some situations that the initial phase could be a random variable. Okay. It doesn't really happen very often in mechanical waves, but it could happen in light, for example. As you learn later, light is due to the emission of photons from matter. And photons are emitted randomly. Okay, nobody knows exactly when a photon is emitted, so that can affect the initial phase, which can be random. So the idea is you want both of these terms to be independent of time, not only the first term, but also the second term. What does that tell us? It tells us if there is any initial phase difference between two waves, okay, phi 1 initial and phi 2 initial, you want to make sure that delta phi is not a function of time. Okay, that is the second condition for coherence. If both conditions are satisfied, then indeed delta phi is not a function of time. So if it's a maximum, it's always a maximum. If it's a minimum, it's always a minimum. We have what's called a stable interference pattern, and therefore we say the two waves are coherent. Okay, we're not going to worry too much about delta phi initial. This will be a big issue when it comes to optics, okay, when it comes to light, because again, the emission of photons is a random event. We're going to worry about it then. For mechanical waves, usually we don't worry about this initial phase thing. We usually just set it to 0 or at least a constant. So just make sure that these two waves have exactly the same frequency and therefore the same wavelengths as well.